let's start with the first sort of most important quantum number, the principal quantum number, lowercase n. Anytime we see lowercase n when we're dealing with electrons, that's the principal quantum number. That's not moles, okay, in quantum mechanics. Okay? Principal quantum number. It's an integer number that is 1 or greater. Okay? 1, 2, 3, and it goes up from there. Okay? There is no n equals 0. The lowest possible n is n equals 1. N, for one thing, determines the overall size and energy of an orbital. Remember, an orbital is what we use to describe sort of where an electron is. So n determines the size of that, but it also determines the energy that that electron has. We talked last time about electrons can only have particular energies. Okay? N will be the main contributor to what that energy is. So let's start with a hydrogen atom. We had a sort of crude drawing before with those big circles. Okay? This is a much better indication, okay, at least it's drawn to some sort of scale, okay, about the various energies that an electron inside of a hydrogen atom can have. And interestingly, the energy of an electron in hydrogen depends only on n. Okay? There are other quantum numbers that influence the energy in other atoms, as we'll see. But hydrogen is really simple. Hydrogen only needs n to tell us what the energy is. So first of all, look at these levels, how they're sort of spaced out. N equals 1 is the lowest energy that a hydrogen electron could have. If it's right there, it's called the ground state. Okay. So if that one electron were to jump up to any of those higher energy levels, those are all excited states. Okay. So, for example, let's say this electron here in n equals 1, let's say it absorbed energy. It would have to absorb one photon. One electron will absorb one photon. That's the particle-like unit of light. And that photon has to have sufficient energy in order to get that electron up to one of the particular other energy levels. Okay? So if it were to absorb a photon that had enough energy to get it up to n equals 2, that electron would then appear in n equals 2 up there. And then it would then release one photon that has the exact energy required to be the difference between the second and first energy level, like that. Okay? So if it were a photon that had much more energy, that electron could have jumped all the way up to 3 or 4 or 5. You'll also notice that they get closer together up here in energy. We'll talk about why that is in a second. And we'll also look at the sign that those energies have. It's interesting how it goes. Okay, so there is a not too complicated equation that defines the energy of an electron in a hydrogen atom. This is for hydrogen only. Because remember we said other atoms depend on other quantum numbers. Okay? But here, energy is minus 2.18 times 10 to the minus 18 joules times 1 over n squared, where n is that principal quantum number. So we just plug in the principal quantum number. That tells us the energy of any of these particular levels. Okay? We could try it for n equals 3. That would be the answer we would get out. You could try it for n equals 10 or whatever. Okay? We will notice, however, that they get closer and closer and closer together the higher that n becomes. Okay? The other thing, oops, restart the program. Delta E, a change in energy. Open up one note again here. There we go. Okay. The energy difference that an electron would have would be the final energy minus the initial energy that that electron had. Any delta is a final minus initial. Okay? So we could actually plug those two energies into this one. Okay? That would give us delta E equals that same constant, minus 2.18 times 10 to the minus 18 joules times 1 over n squared final minus 1 over n squared initial. Okay. That would be just taking this one minus that same thing again and factoring out that constant out in front of it. Okay? So you're given both of those equations, I think. The front cover of your notes. Yep. I say for hydrogen, energy of level n is that first one, and delta E equals E final minus E initial equals the constant times 1 over n squared final minus 1 over n squared initial. Okay. That's calculating the energy. That's calculating the energy difference for an electron that is transitioning between levels. Okay? And that's important because the energy of a photon that's involved in this will be negative the delta E of the electron. And it's negative for the exact same reason we had energy, heat of the system and heat of the surroundings being opposite. Okay? When we're talking about a different frame of reference, what's gained by one is lost by the other. Okay? So that's where that very, very important sign change comes from, right here. So now, because of this, what we can do, we could calculate how much energy a photon would have if that photon was given off by a certain transition, or we could calculate how much energy a photon would need to cause a certain transition. Okay? Let's look at this problem right here. Let's calculate the energy and wavelength. We'll start with energy, but we've got another equation that turns energy into wavelength. Energy of a photon emitted when an electron in a hydrogen atom makes a transition from n equals 3 to n equals 2. We know that that's a photon that's given off because we're going from n equals 2 dropping down to a lower energy level inside of the atom. So that has to give off that excess energy as a photon. Okay? So let's use our equation here. Let's start with delta E of that electron. And just copy that delta E equation, minus 2.18 minus 18 joules. Now, look right up here. I want n squared final minus n squared initial. So what should I put on the bottom of this first fraction right here? 2 squared, okay? Because that's the final. That's the initial. 2 squared minus, okay? So I would like you to get your calculators out, because of about any calculation we do, this is the one that has the most clerical errors. Anybody like to borrow a calculator? Anybody got one? There you go. You need one?
Yeah.
Sure. About there. Okay. Make sure your order of operations is correct over in here especially. You might need some parentheses, and if you especially want to be safe about it, square these out ahead of time. All right. I'm going to type it in just to see what the minimum number of parentheses is. E see if that's right. Okay, so you at least, at the bare minimum, need the parentheses that are here. Okay, because you're multiplying this by that entire summary. But I entered this just like that in my calculator. I said 1 divided by 2 caret 2 minus 1 divided by 3 caret 2, and it worked for me. So the order of operations, the calculator should at least do that correctly. But anyway, what did you get? Minus something?
3.03 to the negative 19.
Yep. I'm going to keep a couple extra digits, 778 or something like that. Okay, but 10 to the minus 19 joules. Okay. And if you didn't get that answer, double check what you typed in. I'm sure you need parentheses here, okay? But be also careful. Wouldn't hurt to put some parentheses inside of here or something, but at the bare minimum, you need those, okay? So that is the energy change that the electron had to do, okay? Negative 3.027, 10 to the minus 19 joules. Okay? The energy of the photon would be what? What would we have to do to get the energy of the photon that is released? What? Yeah, it is the opposite delta E electron. So that is the positive value, 3.03, right? 366, yeah. Probably. Yeah, 2.18. So 3.03, 10 to the minus 19 joules. Okay. Energy of an emitted photon is positive. Okay. So that's given off. It's a certain amount of energy that can be recorded. Okay. The delta E of the electron itself, though, is negative because the electron lost energy. So what else do I want here? That's the energy. That's in joules. That's fine. Calculate the energy. Oh, and wavelength. E equals hc over lambda. Is that one of the equations you're given? Yep. I say E equals h nu equals hc over lambda. In your second column there, so you'll always be given that one. But that will have the relationship between energy and wavelength. And you're going to need to know what lambda stands for. That was actually one of the most common mistakes. I remember people getting lambda and nu, wavelength and frequency, confused from the symbols because the equations just have their symbols. And then the other thing, silly as it sounds, is the algebra to solve for lambda there. What is lambda equal to? Yes, hc over E. I remember being somewhat disappointed last year at how several people solved that saying lambda equals E over hc. It's not right. You do not divide both sides by hc. You would get 1 over lambda there. So you are allowed to swap something on the bottom and the top from opposite sides in an equation, because that would be multiplying by this and then dividing by that. Okay? So hc over E. So wavelength equals hc over E. Why don't you plug those in? See if you get something. See if you get something. And I would like a wavelength in nanometers. Visible light has wavelengths in the hundreds of nanometers. So that's a nice way to check your work, too. But yeah, calculate that wavelength. Tell me what you get. Got all the values you need right there. I've got H and C. What unit will this equation give you an answer in? Yep, I'll give you an answer in meters, because joules cancel, second and per second, and we got meters. And then you got to divide, or you got to multiply by 10 to the what to get nanometers? Yeah, you got to multiply by, well, you would divide by 10 to the negative 9, or you'd multiply by 10 to the 9 in order to get a larger answer with a smaller unit. So, somebody get an answer in nanometers?
6.56 e to the second.
E to the second, which is, yeah, that's right, 650 something. What's it actually rounded to? 6.5, is it 7? I guess it depends if we use this rounded value. If we were being good children, we would do 3.0277 in there. 778 or something like that. Keep a couple of extra sig figs. Anyway, but with the rounding, I got 657. Okay. Now, flip back 2 pages in your notes. Page with the concentric circles. What we just calculated was n equals 3 to n equals 2, and we got 657 nanometers. Where is it? Right there. N equals 3 to n equals 2. That page right there. Should have got 657 nanometers. Okay. What we just calculated was the photon of red light that's given out by hydrogen. Hydrogen gives off pretty much 3, maybe 4. There's one more that's kind of over here. Okay. But it gives off pretty much only those colors of visible light when it's undergoing electron transitions. And we could literally see that by holding up a prism to a lamp with hydrogen glowing in it. Okay. But that 657, that red-orange color, here, corresponds to n equals 3 to n equals 2. And if I make my little colors here, 3 to 2, that gives off red light. A couple of pages ago we saw 486, that was 4 to 2. That was sort of blue-green. Equals 5 is going to be in there. That goes off purple. Okay. But the reason that those are the only ones that give off visible wavelengths of light is because those right there are the right energy gaps in order to give off visible photons of light. Dropping down anything down to n equals 1, that's a huge gap. That's going to be much larger energy, and we're going to be in the ultraviolet or X-ray region. Okay? Dropping anything down to 3, those are going to be smaller gaps. Okay? You can tell that's red. That's at the very lowest energy of the visible light that we can see. So smaller gaps like that will be infrared, and since these ones get closer and closer and closer together, we never really get much more than that. Okay? So, anybody have questions about that calculation? You should actually be able to calculate the energy, the wavelength, or the frequency, I guess, of pretty much the photon corresponding with any transition, okay, between energy levels in a hydrogen. If it was calculating how much energy needs to be absorbed, you would have gotten a positive delta E, and you would have gotten a negative energy for a photon. That's I mean, there is no such thing as a negative wavelength. Okay? So you could translate that into just a photon that needs to be absorbed. Okay? But that's pretty much how that works. The signs end up working totally correct for us when it's a drop in energy and it's a photon that's given off, especially. Okay? So